Universal law of shattering discovered. How objects break predictably for decades. Physicists have observed a consistent pattern in how objects shatter, from dropped plates to breaking waves. Now, a new equation derived by Emmanuel Villermox at Aix-Marseille University in France has codified this phenomenon into a universal law of fragmentation. This breakthrough means that regardless of the material or the nature of the break, the distribution of fragment sizes will follow a predictable pattern. The core principle, maximizing disorder instead of focusing on the microscopic details of cracking, Villermox took a step back. He considered all possible ways an object could break, then identified the most probable outcome, the messiest, most irregular shatter pattern. This approach is similar to how foundational laws of physics were developed in the 19th century, by analyzing large ensembles of particles. The key lies in entropy, the tendency for systems to move toward maximum disorder. Villermox combined this principle with a previously established law governing how fragment density changes during shattering. Together, these components allowed him to formulate an equation that accurately predicts how many fragments of each size will result from a break. Validation across diverse systems to test the equation, Villermox compared its predictions to experimental data from a wide range of shattering events: glass bars, dry spaghetti, ceramic plates, ocean plastic, and even waves crashing in choppy seas. The law held true across all these scenarios, consistently reproducing the familiar graph shape observed by researchers for years. The equation was even validated through a simple experiment involving shattering sugar cubes with his daughters, proving its robustness in everyday situations. Limitations and future directions, the law isn't foolproof. It doesn't apply to highly regular breakage patterns, like uniform droplets forming from a liquid jet, or when fragments interact during shattering. However, for chaotic, uncontrolled breaks, it provides an unprecedented level of predictive power. Ferenc Kuhn at the University of Debrecen in Hungary notes that while the ubiquity of the fragmentation pattern suggested an underlying principle, the law's broad applicability is remarkable. He also points to the equation's adaptability, noting that it can be modified to account for specific constraints, such as the self-healing cracks sometimes observed in plastics. Real-world implications understanding fragmentation isn't just an academic exercise. Kuhn suggests that the law could have practical applications in fields like industrial mining, where optimizing the shattering of ore can improve efficiency. It may also aid in predicting and mitigating rockfalls, which are becoming more frequent in mountainous regions due to rising global temperatures. Future research might explore the distribution of fragment shapes, not just sizes, and determine the theoretical minimum fragment size. For now, Villermox's equation stands as a landmark achievement in understanding one of nature's most common yet mysterious processes. The equation doesn't work in cases where there is no randomness and the fragmentation process is too regular, explains Villermox, emphasizing the law's dependence on chaotic breakage.